Hello, my name is Lars Pachoki, and I will be presenting Fermat's last theorem proof for n equals 4. So, one thing that's probably very familiar from high school is positive integer solutions of a, b, and c for a squared plus b squared equals c squared. This is very familiar. What's unfamiliar is positive integer solutions of a to the n plus b to the n equals c to the n for any n greater than 2. And why we are very unfamiliar with that is actually because no integer solutions that exist. The idea that there was no integer solutions was proposed by Pierre de Fermat in 1630, but he never actually ended up publishing a proof saying that there were none. Eventually, the proof was shown by Andrew Wiles in the 1990s after decades of research into the subject. Before I actually get into the final proof for this, I will be showing other proofs that we will use in this. So I'm going to prove Euclid's formula for Pythagorean triples, and I'll show you what those are. So a Pythagorean triple is made from a squared plus b squared equals c squared. So a squared over c squared plus b squared over c squared equals 1. We get that from dividing each side by c squared. Let's define a point P. P will be at x sub 1, y sub 1. And that will be of coordinates a over c, comma b over c. First thing you'll notice is that a over c and b over c, if we take the distance from this point to the center, it will be 1 by definition from this right up here, which you can see with my cursor. Other thing you'll notice is that this has to be in the first quadrant. Since a, b, and c are all positive integers, when we divide them, we will get positive numbers, meaning that it will be in the first quadrant, since x and y have to be positive. So let's define a point Q at 0, negative 1. So therefore, the y-intercept of, if we make a line QP, is obviously negative 1 from right here, from point Q. If we take the slope of the line, we take y1 and x1, and we trace that back to Q, and we take y final minus y initial over x final minus x initial, we get this right here. The equation of the line, we put in y equals mx plus b, plug in the slope, plug in the y-intercept. Then let's also define a point R. Point R will be at the intersection of line QP as well as the x-axis, which obviously has y-intercept 0, since it intersects the x-axis. Therefore, we can go ahead and plug the formula for the line in for point R at k, 0. And let's go ahead and we end up going and getting this. Once we add 1 to each side, we can end up multiplying by the inverse of this, and we find that k is the inverse of the slope. Then let's go ahead and let's take line QP and end up solving what that hits the circle. That will give us two solutions. One is point Q, one is point P. Let's solve for point P and see how else we can write point P. We take the formula for the line, we can put it in terms, slope in terms of k, and let's go ahead down and solve. And when we go ahead and down and solve, we get x in terms of k and we get y in terms of k, right here and right here. Then we can say that k, we can define it as n over m. We can define k as n over m because we know that k must be rational, since it's constructed from dividing rational numbers over and over again. So since now that we know that k is rational, because it's x sub 1 over y sub 1 plus 1, and we know that those are rational because it's defined of dividing these positive integers, we could go ahead and say that it's equal to some fraction n over m, simplified fraction, where n and m don't share any common factors, so it's all simplified. Then we can replace k with n over m. Go ahead down and solve for y, and go ahead down and solve for x. So we get y equals this right here, and x equals this right here. They both share a common denominator, and you know that y equals b over c, defined earlier on over here, and x equals a over c. We can make the common denominator c and make the numerator equal to b for y and the numerator equal to a for x. So c equals n squared plus m squared, b equals m squared minus n squared, and a equals 2mn. Since n over m was a simplified fraction, we can say that n and m must be coprime. This means that they share no common factor. That's what coprime means. And we said that they didn't share a common factor since it was a simplified fraction. Let's keep this in mind. This will be useful for our proof. Now, let's go on about coprime triples. So if we are given a Pythagorean triple a squared plus b squared equals c squared, either a, b, and c are all coprime, they share no common factors, or none of them are coprime, and they all share a common factor. So let's say a and b aren't coprime. This means that they share a common factor. Let's just say that's d. When a and b are factored by d, they must, by definition, give integers since they are factorable by d. Let's define them as alpha and beta. So a over d is now alpha, and b over d is now beta. So from a squared plus b squared equals c squared, we can say a is the product of alpha and d. So we can change this into alpha squared of d squared plus beta squared d squared equals c squared. Factor out a d squared. We get alpha squared plus b squared. This is obviously an integer since we know that alpha is an integer and beta is an integer. So this integer solution equals c over d squared. So c over d squared has to be an integer, which means that c over d must be an integer. So c must be divisible by d, making nothing coprime since they all share this common factor. We can do very similar going down with case 2, a and c not being coprime, and you'll find that b has to be not coprime with all of them as well, or b and c are coprime, which makes a not coprime with all of them as well. So either they're all coprime or they're all not coprime. Let's go ahead and start the actual proof right here. I'm going to do a proof by contradiction. So back to what this was. This was a to the 4 plus b to the 4 equals c to the 4. We wanted to show that there was no solution for that. But let's assume that a to the 4 plus b to the 4 equals c to the 4. There exists a set of integers a, b, and c that would solve this. So given that there is a possible solution, there must also be a minimum possible c solution. In the case of 3 squared, in the case of a squared plus b squared equals c squared, the minimum possible c is 5 in 3 squared plus 4 squared equals 5 squared. There has to be a minimum possible c, because if we look at a number line, you'll go ahead and see, okay, does 1 work? No. Okay, well, does 2 work for c? No. Does 3 work? You keep going up. There must be a minimum possible point at which it works. You can't have it infinitely approach 0 because there's not infinitely many numbers to go and approach 0. There's a finite number. So there is a minimum possible c that works. Let's define c squared as w. And let's define w as the minimum possible c squared. So we have a squared plus b squared equals w squared, where w is the minimum possible one where this works. This can be rewritten as a squared squared plus b squared squared equals w squared. We also know that a squared and b squared and w are coprime. This means they share no common factors. Why don't they share any common factors? Because if they did, we could cancel it out and w wouldn't be the smallest possible solution for this. Since we have a Pythagorean triple since we have Pythagorean theorem right here, a squared squared plus b squared squared equals w squared, this means that we can use Euclid's formula back to get these other things derived from it. Because when we have Euclid's formula right here, we can derive these things from a squared, b squared, and c squared. Now a squared is 2pq, b squared is p squared minus q, and w is p squared plus q squared. We know that p and q are coprime because when we look at this, n and m must be coprime. When we take p and q from w, they are also coprime. Therefore, p, q, and w are coprime from looking at the coprime triples, when we said that they're all coprime or none of them are coprime. We can obviously see another Pythagorean triple right here, b squared equals p squared minus q squared, which we can write as b squared plus q squared equals p squared to look more familiar. Since this is a Pythagorean triple, we can use Euclid's formula again to derive q equals 2rs, b equals r squared minus s, and p equals r squared plus s. R and s once again form that fraction that we set over here. Therefore, they are coprime. Using coprime triples, we know that p is coprime with r squared and s squared. and therefore P is coprime with R and S. Knowing all this, let's go and move on to something else. So we know from before that a squared equals 2pq. So a squared equals 2p. What is q? Q is 2rs. So a squared equals 2p 2rs. Okay. Or a squared equals 4prs. Let's take the square root of each side. We get a equals 2 square root of prs. Knowing this, we must know that p, r, and s, the square root of each of them, is an integer, because we can't share factors when multiplying together. If they did share factors when multiplying together, if let's say p was divisible by 2 and r was divisible by 2, and therefore by multiplying it together, we get a 4 in there, take the root of 4, it's 2. So that ends up simplifying out. We can't do that. Why can't we do that? Because they're all coprime with each other, which we said right up here. Because usually if we have 18 and 2, 18's factors are 3 and 3. 3 times 3, we can take out a 3. 2, and let's say r is 2. So 2 times 2, we can take out a 2. We can't do that because they each have to have their own set factors since it's coprime. So since they're all coprime, there's a set uij where u squared equals p, I squared equals r, and j squared equals s. This is restating the same thing for integers u, I, and j. So now we know that p equals r squared plus s squared. This is back from right up here. What is p? That is equal to u squared. What is r squared? That's the same thing as I to the 4 from right here. What is j? What is s squared? That's equal to j to the 4. And you'll notice that u squared equals I to the 4 plus j to the 4 is very similar to a to the 4 plus b to the 4 equals w to the 4. And the other thing you'll notice is that u squared is actually less than w squared because we kept taking smaller and smaller terms from finding what w is equal to p squared plus q squared, and then p squared is r squared plus s squared. So you keep getting a smaller and smaller until we have this really small u squared, which is an integer solution for this. But w was supposed to be the minimum possible. We defined w as the minimum possible to solve this. But you'll notice that u is actually a minimum, is even a smaller number that ends up solving it, which contradicts what we entirely said. So how is this contradiction in logic possible? It's possible because what we assumed was wrong. And what we assumed, the one thing, was that a to the 4 plus b to the 4 equals c to the 4 had a solution that existed for a positive integer set of a, b, and c. Therefore, there is no positive integer set a, b, and c for n equals 4 for Fermat's last theorem. Here are my works cited for various arguments that I used going through here of people that helped me write all this down and things on the internet that helped me write all this down. And here are the citations for the pictures. Thank you.